The title of this talk is Community Continuous Integration for GNU Radio and OpenCPI. Hi, I'm Arlen Poole. This talk builds on the previous talk, OpenCPI is an infrastructure for GNU Radio. OpenCPI brings the capability for GNU Radio applications to exploit the hardware of embedded heterogeneous processing systems and be deployed on diverse hardware. In the first part of this talk, I'm going to present how do you assess whether your OpenCPI application is ready for diverse hardware. In the second part of this talk, Willie Thompson of Centauri will present a case study of enabling a GNU Radio application to exploit OpenCPI. For this case study, he's going to use the GNU Radio ADS-B receiver application. When is a GR application ready to deploy on diverse hardware? That determination requires that the developer have access to a diverse set of development and testing hardware assets. In most nearly all cases, the developer will not have direct access to a variety of different hardware configurations. In seeking to address this issue of developer access to a set of diverse hardware assets, the OpenCPI team has a roadmap with two CI facilities. The first is a dedicated CI hardware test center for continuous testing, and that's separate from the dedicated development lab to support OpenCPI and software and support platform development. The focus of this talk will be on the Community CI Test Training Lab. As I mentioned on the last slide, we have a dedicated CI hardware test center for OpenCPI continuous testing. Continuous testing for both OpenCPI and supported hardware platforms. This is a dedicated CI hardware test center that exists today. It's a stable, lights-out resource with configuration control. Hardware-in-the-loop testing is being added for additional supported platforms, and testing scalability is provided using AWS. Assets include supported hardware devices and platforms, the required versions of software tool chains and simulators, and supported versions of operating systems and system software. OpenCPI's CI testing strategy exploits OpenCPI's heterogeneous unit test system, uses Gitlab's CI tools, and baseline testing is kicked off by commits and merge requests. Full build and tests are performed on weekends, and this delivers a continuous test coverage for OpenCPI software and gateware on all supported hardware. As I mentioned a bit earlier, the OpenCPI roadmap includes a community CI test and training lab. The first instance of this community resource is the GRCon20 OpenCPI workshops. We're standing up this workshop lab as an initial dry run to the community, and the workshop lab is populated with 20 plus of the analog devices, Plutos, an EDIS E310, and Linux servers. There's remote access is controlled through a VPN. This is really a prototype for our community resource. We're gaining experience with both requirements and implementation. After GRCon20, we will transition to a more complete capability and have policies for access control and scheduling and populate it with additional hardware. The ultimate objective is for assets to include all supported hardware plus third-party provided hardware that's either co-located or remote. This provides community-controlled access to third-party provided hardware. This Community CI Test Training Lab will provide different benefits to different stakeholders in the GR OpenCPI community. The stakeholders who will benefit include GR block and OpenCPI component developers, application developers, prospective users and projects, and also hardware vendors and integrators. Now I'm going to address how each of these parties will potentially benefit from access to a community resource. The benefits for GR block and OpenCPI component developers' access to a community CI test training lab is that it allows the testing of blocks and components on a diverse set of hardware that they may not otherwise have access to. This helps ensure overall portability, and developers can perform both unit testing and development and testing of example applications. It also allows testing across multiple processor architectures and configurations to characterize both performance and resource usage. The benefits for application developers of a community CI test training lab is that it allows them to test applications on a variety of hardware configurations. It allows experiments to be performed with different hardware configurations, such as a general purpose processor and FPGA implementations, to assess performance and resource usage. This improves the readiness to support future hardware configurations, as these experiments have provided additional insight into both performance and portability. The benefits for prospective users and projects of a community resource is it allows the prospective users to gain clarity into the supported hardware configurations and their stability, sort of a kick the tires. It also allows them to test available components on candidate hardware and do some experimentation with different hardware and hardware configurations to understand what may be most suitable for their application requirements. It also gives them an insight into performance and resource usages. The benefits of community resource for hardware vendors and integrators is that by providing access to their platforms, hardware vendors can ensure that their platforms get tested and characterized as both GR and OpenCPI evolve and as their hardware evolves. Prospective users then can assess the vendor-provided hardware, and applications can be characterized on custom configurations and platforms created by system integrators. In summary, the Community CI Test and Training Lab is going to provide benefits to the overall GR OpenCPI community. The use of the Community CI Test Training Lab enhances the readiness of GR OpenCPI applications to support diverse hardware. Now I'm going to turn it over for part 2 of the talk for an OpenCPI case study, which will be presented by Willie Thompson of Centauri Corporation. He's going to talk about enabling the GR ADS-B receiver application to exploit OpenCPI.
Hi, my name is Willie Thompson. I'm a senior cybersecurity engineer from Centauri. I will be presenting our OpenCPI case study for the ADS-B receiver. This briefing serves as a primer for a detailed discussion, a part of the OpenCPI workshop. Over the last several years, ADS-B has been used as a good reference design to demonstrate different GNU Radio applications. The key aspect for the receiver is being able to detect the preamble and then demodulate the post-position modulation. For our design, we'll be concentrating on the 180-bit mode S message. The fundamental question for this community is why OpenCPI? OpenCPI provides a flexible framework for component-based design using multi-layer specification for components and workers and interface specification for custom protocol design. In addition, it supports heterogeneous operation. You can design for GPP, FPGA, or GPU. And lastly, OpenCPI supports deployment across new platform types. This allows for the optimization of algorithms for increased performance. The primary goal for this case study was to translate a GNU Radio implementation of the ADS-B waveform to a OpenCPI embedded device. During this process, we was able to develop RCC and HDL component libraries to support heterogeneous operation of the waveform. In addition, we leveraged the OpenCPI system support projects that support several platforms, including the E310 and the Pluto SDR. The hardware demonstration will be a main focus in the OpenCPI workshop that will be given later on in the week. The first step is the OpenCPI component definition. For our use case, we actually concentrated on a one-to-one relationship between the RCC and HDL worker implementation to support heterogeneous operation. But this is not always the case. It really depends on what type of deployment strategy you will have on the embedded system to dictate what type of workers you require for the different components of your waveform. During the OpenCPI component definition, there's two levels that you have to define. The first level is the OpenCPI component specification. At this level, you focus on the port definitions. In particular, you implement a OpenCPI protocol specification. This specification defines the opcode, format, structure, data bus of that interface. Each interface can have the same protocol specification or can have a different protocol specification. In addition, you actually define your component level properties. These properties are properties that are associated with both type of workers, RCC and HDL. The different worker types can have additional properties and parameters defined. And that definition specification is called the OpenCPI worker description. The worker description for the HDL is very important. In particular, for the HDL workers, you have to define your port width, which is not the case for RCC workers. So you definitely will have to define your worker description interface attributes for each port width, bus width that you use for your input or output or any interface that you have with your HDL worker. Lastly, we actually did a data rate analysis doing this component definition because we were really interested in heterogeneous operation, and based on the different worker types, you may have bottlenecks that you have to take in consideration when going from a RCC worker to a HDL worker. So we strongly encourage you to do some initial data rate analysis doing the component definition. As you can see with the diagram above, we actually highlighted the samples per symbol throughout our algorithm. We actually defined the component level specification. Each of these may have additional worker description definition associated with them. In addition, we are looking at Q15 data notation throughout our algorithm for the ADS-B. Next, I will highlight the RCC development for our case study. Here is the basic anatomy of a RCC worker, which consists of three main elements: buffer management, the work implementation, which is the run method of the RCC worker, and then finally the work return value, which is a RCC result data type. For buffer management, we initialize pointer to the buffer object associated with each interface. Each buffer object has several methods associated with it. In this case, we're using the size method to attain the buffer size of the input buffer to be used during the work implementation. For the work implementation, we need to process several opcodes associated with the protocol specification. The main opcode for this worker is the sample operation, as shown within the case statement code. For the sample operation, we simply multiply the input buffer values by a constant. This constant is a property of this worker, and we obtain the value of that constant through the properties method of the worker. For the other opcodes, we do nothing. We simply pass the input buffer to the output buffer for further processing down the line. Lastly, we must return a value for this worker. The RCC result data type has several values. The three we highlighting here is the RCC advance, which advanced the buffer to be used again. So the output buffer is processed out of the worker to be used downstream, and we obtain new data within the input buffer. The RCC done actually enters the worker into the finished state. Lastly, RCC advance done actually advance the buffer and enter the worker into the finished state. For our case study, we actually leverage all the work implementation of the GNU Radio library. Next, I will highlight some key aspects of our HDL development. Our HDL worker design methodology is based on a OpenCPI wrapper scheme. This wrapper scheme allows us to use standard VHDL development flow for the work implementation. Once the work implementation has been verified, that code can be wrapped into a top-level design. The top-level design focuses on the OpenCPI integration, which is primarily worker operation control. OpenCPI operation control is based on several metadata signal. For this design, we have a do work signal that is conditioned by data validity and work availability. In particular, we are using the valid signal associated with the input interface to indicate that the data is valid for operation, and we're using the ready signal associated with the output interface to indicate that the data can be accepted by a downstream worker before we actually do work. In addition, we are implementing a data plane scheme, which is new for OpenCPI 2.0. In this scheme, you can associate a clock with an interface. As a result, we can use that clock to actually run our worker. To enable this functionality within the framework, you have to use the worker description attribute clock direction. More detail can be attained within the user guide. One additional concept that we want to highlight for the HDL development is the concept of assembly and containers. Assembly containers are needed to create a bit file. The assembly is actually all the HDL workers associated with an application. So when you have an OpenCPI application, there should be a one-to-one relationship between the application that use HDL workers in the assembly. In addition to the assembly, based on how you want to deploy the actual application, there's a container. That container allows have additional device workers that are used to actually execute that application on that platform. The containers are associated with the board support packages of the different platforms, and for simulation, the XM is considered a container that simply execute the code. Here's a depiction of our OpenCPI application for the ADS-B receiver. You can see that it have all the elements associated with the waveform. This is a hybrid design where we have HDL workers, which is a part of our assembly, and then we have two RCC workers to source and sync the data for this application. Lastly, we will talk about some OpenCPI component libraries that have been generated by this case study. In support of growing the community around OpenCPI, we have created several libraries that is open to the community. The first one is a general SDR component library, which you can see is divided into several different types. It's really the RCC workers are really closely aligned with GNU Radio. In addition, we are actively developing HDL worker for these elements to support heterogeneous operations. In addition, we have two application-specific libraries associated with this work. That's the ADS-B, and also we have created a ZigBee library. All of these libraries will be pushed out to the community at sometime soon. As the third-party evaluator, we were asked to give our final thoughts on OpenCPI based on our case study. OpenCPI is a unified framework for open source heterogeneous design and deployment. It provides a flexible XML framework that describes all aspects for component, application, and platform. Throughout this presentation, we highlighted several of these specifications. It is our opinion that they are easy to understand and to implement. RCC development and operation is GNU Radio Lite. OpenCPI supports external libraries for rapid development. In particular, for this case study, we leverage the GNU Radio code base. Opcodes are similar to GNU Radio stream types. And finally, OpenCPI implement buffer-based operations for RCC workers. Next, OpenCPI fully integrate HDL tools for development and simulation. For our case study, we leverage standard VHDL development flow for worker verification. OpenCPI integration focused on worker operation data flow via OpenCPI metadata signal. Third-party HDL primitive and IP cores are supported. Finally, OpenCPI allows for the deployment of application across multiple embedded platforms. For the ADS-B application, we are looking at the Pluto SDR and the E310. In addition, we are developing an OSP for the N310. For further detailed discussion about this case study, please join us at the OpenCPI workshop.
Thank you, Willie, for that presentation. As you can see, OpenCPI as an infrastructure for GNU Radio brings a lot of new capabilities that we believe are interesting and exciting for the GNU Radio community. For additional information on OpenCPI, please see the list on the screen. I'd like to take this time to thank the GRCon organizers and thank you for listening to my presentation.